Hello, my project is about bio-inspired and smart blade designs for more efficient and resilient wind turbines, and also the preparation for implementing CFD on my blades. So, you may be wondering why I'm interested in this topic. So I'm interested in this topic because there's a need for more renewable energy, especially wind energy. I've noticed that there is a severe increase since the 2000s in the use of wind energy, and it's getting a lot of attention, especially nowadays. And I was also I'm interested in this topic because I was curious to know how they work. I always liked seeing them when driving, and I wanted to see how they worked. So, what a better way to do that is by conducting a study. So where's my idea from? So since I was younger, me and my family we would go to museums and I would see like an energy section about renewable energy and wind turbines, and I would always be amazed by how everything worked. And since then, when I wanted to think of an idea for the science fair, I thought about something uh, that had to do with wind turbines, and I decided to make designs, blade designs that are bio-inspired and smart. So, what is my problem, and how did I choose a solution? So, my question that I wanted to answer was, how can I improve the efficiency and resilience of wind turbines? So, the efficiency of wind turbines low wind speeds is not as good. So they'd have to be placed at high levels, which would be cost effective for the materials. Also, during severe wind conditions, the wind turbines would have to they would be damaged. Some of them would be damaged, and the generator would overflow, and that would be very expensive to replace. So, what is the science behind my study? So, this study consisted of many science and engineering concepts. It was an it was important to understand like basic physics, fluid dynamics, and aerodynamics. There were several equations involved in my study, such as power coefficient, Bernoulli equation, lift force, and many more. And so what I was trying to do is increase the Reynolds number, torque, lift to drag ratio, and power coefficient, which is the most important one. And what I was trying to decrease was the drag force and boundary layer separation. So now to my methodology. I used a 12 centimeter wind tunnel and motor to test my blades. The wind power was measured by using an anemometer. The power output was calculated by measuring the voltage and the resistance using a digital multimeter. A 3D printer was used to print out the hubs for the different twisting angle, and the bottoms of medicine bottles were used to make the hubs for the 45-degree and 90-degree cone angles. And for the seriation, which is bi-inspired, I used a soldering iron to make them. So for the drag force, I measured it using a drag force tool and a scale, and I also used variable power supply to maintain the wind speed fixed in the wind tunnel. The parameters tested were some of them were like blade shape, diameter, seriation, which was one of the most important ones. Cone angle is also an important one, which is the smart one, and I also had a few other ones. So now let's focus on the bio-inspired part of my study. So the one to the left is a brown bobby bird, and the bio-inspired part from that was the wings. I made my some of my blades were shaped like the wings of it, and for the humpback whale, you can see the fins are kind of like bumped, and that's where my seriation came from. And lastly, you can see that this flower. I'm not sure what they're called, but it's bio inspired for my cone angle. So my cone angle is basically um, it's basically two angles in one blade. So there's 45-degree angle which is spins, and 0 degrees which doesn't spin. So when the wind conditions are beneficial, good air, the propeller can open up to like 45-degree angle where the propeller can spin. And then when the wind conditions are bad, or like they can possibly damage the wind turbine, it will just close up, and it won't spin, and that would help with it not getting damaged. So now let's move on to my results. So the first thing I changed was the shape of the propeller and propeller age, which is a 11 7 centimeter blade, it produced about 824 milliwatts. Next, I have the diameter with and without seriation. So you can tell I have seriation and no seriation, but unfortunately, this really surprised me. The ones with no seriation did better than the ones without seriation, and that really surprised me because, like in other studies, that was supposed to improve the blade. And also, maybe I don't think I don't think that should be from the results. I think it should just need more optimization because I used a soldering iron. So maybe if I did it in a CFD, when I do it in a CFD, I'll get better results, hopefully. Moving on to the cone angle, I changed the cone angle. So the cone angle is basically the bi-inspired. It's basically the one that closes and opens to like 45 degree and 0 degree angles. And the one with the 4 centimeter non-seriated one did best. Onto the airfoil curvature. This wasn't very important in my study since it was not, the results were basically relatively the same. I changed the number of blades, also the concaveness. So I decided it was pretty obvious my results, but I just gave it a try to see if there was going to be a change, but they're all pretty much the same. Um, Pretty similar with the number of blades and seriation. The number of blades isn't really something big, like 2 blades is basically like 6 blades. Like why use 6 blades when you can use 2 blades? Because when you're using 6 blades, you're using more materials, which is more expensive. And same with the seriation. The seriation did also make the blade better worse in this part as well. And lastly, I have the aerodynamic analysis. So I measured the aerodynamic analysis when the blades were fixed and when they were set free. And as expected, the ones that are fixed did gave a lower drag force, which is better, which is more beneficial. The less drag force, the better for the blades. So you may be wondering, if I repeated my study, what would I change? So you've heard me when I say the seriation didn't do as good. So the first thing I would do is re-optimize my blades to make them even better. Maybe do the seriation one again and redesign my blades seriation to try to improve it. I would maybe add more perimeters like the tip speed. And lastly, something I may do maybe in the future is measure the torque. So in conclusion, using smart and bi-inspired designs as a part of my study, I realized that that was very beneficial. And there were some unexpected results like the seriation, but it may be just in the optimization. And that's what's fun about science, you know. Not every result is going to come out as expected, and that really surprised me. So what's next? For what's next, I'll be using a I'll be re I'll be testing my blades using a CFD. And I already started with this part. I'm currently learning how to use a CFD and studying how CFD works. So I may be wondering, what is CFD? So CFD is basically a simulation on a computer, usually for fluid dynamics. It could be anything that has to do with fluid dynamics, and it consists of engineering, specifically fluid dynamics, a very complex computer science, and also very complex mathematics. And for the solvers, these are some of the CFD solvers. There's OpenFOAM. OpenFOAM is one of the solvers, and there's Star CCM, and lastly ANSYS Fluent. So during the in the articles that I analyzed, ANSYS Fluent was the most commonly used. So CFD literature review. Sorry. So CFD can be an alternative to doing experimental methods. So I analyzed 50 papers. I summarized 50 journal papers, and I searched for those papers using Academic Search Complete Database. And I found my articles from there. And I obtained more than 50 journal articles that I summarized about CFD and wind turbines. And after doing that, I narrowed it down to about 20 of the most important papers that I can use to learn more about CFD. And I specifically selected the ones that compared results of experimental and CFD analysis. So for my metadata analysis, I chose to study the ones for tip speed ratio and seriation. I'm currently doing a metadata analysis, uh, and um, yeah. I also extracted the results of those studies for learning about for learning more about them. So this is one of the studies that did a CFD analysis. They compared the experimental and present study, which is CFD, and you can see that there is a trend, and it's pretty similar. And this is another one. This is basically applying geometrical applications to CFD to wind turbines using CFD, and this study is actually from 2021, so it's pretty recent. And then this guy from the study made compared 2D and 3D CFD. So 2D and 3D CFD, they're pretty close, but then 3D is more accurate, but they're still close enough in the results. So like because 3D requires more computer performance, uh, 2D is better for 2D is better because it requires less performance, and you can see it's pretty close. So for those trying to do CFD, they don't need a big they don't need a very a powerful computer. So based upon the knowledge that I've learned, how can this benefit the society? So this can benefit society because it can increase the use of renewable energy, especially wind turbines. It can also encourage people to start using CFD, or they can use CFD for any fluid dynamic project. And there, this is good for making wind turbines more resilient, and this encourages people to use wind turbines more. And one of the big ones is reducing costs. So one of the main reasons not a lot of people have wind turbines is the cost. They're pretty expensive. So if we can reduce the cost, that would make people use them, and overall that would be good for the environment. So this is my project that I just presented, and I hope you like it. And yeah, that's it. Have a good day and bye.